Cool. Hello. Well, yeah, so today I'm going to talk about a paper that I really like called ACLs Don't. You see, it's got a catchy title. That's just by Tyler Close. Just briefly about me. So although I'm a Londoner, I actually live in Cambridge now. This is Cambridge. This is just down the road from where I live. So I kind of like this. I like to go walking around here in the evenings. This is the Institute of Astronomy radio telescopes, where just around where quasars were discovered 50 years ago last year. Cambridge is sort of science village, really. It's very close to London, very nice place to visit if you happen to be around. I work for Docker as a security engineer. This talk is not really about things I do for work, although actually I kind of might mention a few things kind of towards the end. But so this paper, it's this paper here. It was I came across it maybe about 4 or 5 years ago, I think. I kind of always remembered it. It turned out that many other people did too. It was a Hewlett-Packard Labs technical report back in 2009, and it was apparently. It says on the notes it was submitted to the IEEE Symposium on Security and Privacy. I went through the conference proceedings and I couldn't find it, so I guess it was not accepted, which is kind of interesting. But anyway, they released it as a technical report. And just kind of why I like this paper. I mean, it's short. It's like 10 pages or something like that. So it's really short. It's incredibly readable and well written and just clear about everything. And I always enjoy things that are just understandable. You know, it's not full of maths or anything. It's just got a few little diagrams, a few little things, and it kind of points out why things are not the way you think they are. And it makes you kind of think about the problem. And I think that's what's really interesting about it. It's a bit of a sort of underground cult paper, I think. So you can kind of join this underground cult. I've met other people who've read it, and they also think it's amazing. And the problem is talking about access control is really, really important. I mean, I work in security and I think it's important, but people who don't work in security think it's important too, because you don't want people accessing your stuff when they shouldn't. That's an important problem. It's like, you know, everything's straightforward if everything's just public, but then that's not the real world. Things are not public, things are private, and people want access control. And making access control work on computers turns out to be actually kind of hard. And this paper talks about some reasons why it's hard, and the lessons have not really been learned 10 years later. So that's interesting too. And some things have changed, and some things haven't changed. We'll talk about those a bit. I'm going to talk about the paper sort of in the first half, and then the second half I'm going to talk about kind of the world we are now and what's changed and what hasn't changed. So my nice little white box that was covering up the little bit of text has just come out as with this nice thing around it. That's a bit annoying. So I should have... Anyway, so the kind of paper, the sort of setting the scene in the paper, it starts with this thing about how there were all these kind of straightforward security issues that appeared, like buffer overflows, and we can get rid of buffer overflows by writing everything in Rust, as we all know. And SQL injections, we can, you know, not concatenate those strings that the user gives us. But these were all kind of straightforward things, and they just, you know, injected things in the program that was running. It was obviously something wrong was happening. But then he points out that there's recent things that happened. This was recent in 2009. Things like cross-site request forgery turns up and clickjacking. And no code gets injected. Nothing's doing anything weird that it shouldn't be doing, apparently. Like, there's no obvious bad hacker attacking your weak program and making it do things it shouldn't do. It's actually, you're just using a program, but you're using it to do things it shouldn't be able to do. You know, it's a legitimate request, apparently. It's like coming in, and then, but it gets access to something it shouldn't have access to. And that's weird, because that's not how you expect kind of security things to be. They're not supposed to be legitimate requests where something bad happens for no apparent reason. And this is kind of the scene he sort of sets. And he refers back to a kind of an example and an access control measure from a paper back in 1970, referring to some work that was done I think in the 60s. So the kind of background of how we think about these problems is really quite old. And so the example is quite old, quite traditional, and so the example that he uses, which is the one from the 60s, is this compiler service. And it's actually, I think he kind of apologizes for using the old example in the paper because it seems a bit weird to modern users. But it's kind of, now it kind of makes more sense as a kind of microservice or serverless thing, I think, in a way. And so I'm going to kind of refer to it in that way. But I haven't changed the names of things too much for the example. So some cloud vendor is selling you a compiler that you the user, you're going to feed your program, which is called main.c, because for some reason you're still writing in C. And it's going to output something called a.out, because that was what compilers back in the 60s called all the programs they compiled for. And it's still the default with C compilers. And it's going to output a log file. And I think from in the original paper, the log file was the billing records for how much they were charging you for using this compiler. And that's a kind of, we'll think of it like that. So the vendor, let's call them Amazon, say, are going to bill you to use this compiler that they've got in the cloud. You're going to give them a program and they're going to give you the compiled output and you're going to pay them some money. So that's the kind of model. And let's imagine that these files are going to sit in S3 buckets, because that's kind of the kind of model we want to think about in this. And so you have access to read and write your program in your S3 bucket. And then you can read and write the S3 bucket that you're going to write this a.out program to. And the vendor, Amazon, can write to their log file that says how much they should charge you for using this, and you can't write to that. So this is the kind of traditional pattern of how you look at access control for this problem. But we're going to make a compiler, and we're going to imagine this compiler is actually, we're going to create a Lambda just for you for this to compile this one program, because that kind of makes it kind of easier to understand. So you're going to create a compiler instance, and it needs to be able to read your program to compile it, and it needs to be able to write to the output once it's done that, and it needs to be able to write to the log file in order to write how much it should bill you for doing that one compile job. So it's 1,000th of a cent or whatever it might be that Amazon's going to charge you for running this compiler. Often people won't run something in a situation like this. If you're running a compiler on your laptop, say, the compiler might actually have more permissions than that. You might just give it, you might just run the compiler kind of as your own user. It might actually have read and write access to all the files on your entire computer. But in a situation where it's not want to give it read and write access to everything that you have in your whole world, like your photographs or anything like that. You just want to give it access to the thing you want to compile. So there's this whole kind of principle of least privilege, which is really important, which is don't give it stuff it doesn't need. And that's a really important security principle that we're going to assume at the moment that we're implementing correctly and well, but we're going to talk about that a little bit later, because often that isn't the case, and that isn't how this is done. So this is how we're going to set up this compiler so it can do those things. And this all looks nice and it all looks good. It can only read the input and write the output and write the log file. Yes?
What is the vendor
The vendor owns the log file. The vendor is Amazon Web Services, and they own the billing log for Amazon, and that's their kind of thing. So they, yeah, well, it's their, they own it. They own it basically. But the compiler needs to write to it because it needs to say, I did do this compile for this user. We need to bill now. Apparently, the billing system at AWS is the largest and most complicated system ever built in the entire universe. And previously, this was reserved for telephone companies' billing systems. But Amazon, of course, became enormously larger than all the telephone calls in the world that had ever been made very quickly. And their billing system is absolutely gigantic. And obviously, they say with telephone companies that the billing system was where all the engineering work went, because that's where the revenue comes in. And if it goes wrong, they don't mind if your phone call goes wrong, but they do mind if they can't bill you for it. So billing systems are kind of fascinating. So this paper is talking about two implementations, and the first one is the kind of very traditional access control model, and I've taken this from the paper. So effectively, the stage that happened is that the user tells the compiler to compile main.c to a.out. So the compiler, we know it can read main.c, so it can read that. The compiler can then append the log entry, which is the billing entry, to the log file, and then it can write the output. Always write the billing information first, because you don't want, if you crash after you've written the output before you build, that's the wrong way around. And then you write the output once you've actually written the billing entry. So and if it crashes after they've written the billing entry before you get that, then presumably you send a complaint in. Then the alternative to this that the original 1971 paper talked about and basically said was basically the same thing was the capability model, where each of these messages includes permissions on it. And so the thing that people were most familiar with in terms of this is file descriptors in Unix. So I've kind of written this entirely in terms of file descriptors, but because file descriptors are a kind of capability model. You can't run this on Amazon because Amazon doesn't support file descriptors. But effectively, what you do is you say, I open a file and hold on to a reference to it, the main.c and the a.out as the user. The vendor opens the log file. The vendor creates a new compiler, which I'm going to use. I tell the compiler to compile given those two file handles, so it has access to them. The compiler reads the file, and then it appends to the log file that it was passed the capability from the vendor, and then it writes with the capability I gave it. And so this is a kind of, I'll talk a little bit later about how you actually implement this in AWS. So this is a kind of different thing. So instead of giving it the name of the file and it having permission, I give it something that it can use to just access that file. And we'll talk about that a little bit. Yeah.
In that case, there is no global namespace of file descriptor.
No. So, in fact, I'm talking about this now. I forgot. So, in AWS, you can do this by passing signed URLs to S3 buckets. So imagine those things are signed URLs that say you can write to this bit of this S3 bucket, or you can read from this bit of the S3 bucket. And so that's the kind of AWS equivalent of that. Whereas the ACL model is creating a Lambda which has write access to that S3 bucket, and write access to the other S3 bucket, and read access to your S3 bucket, and then you create that Lambda for that one thing. We're going to talk about this kind of real-world model in a bit. So at the moment, these look like they do the same. I mean, they do the same thing when everything's working correctly. But this confused deputy problem says, if the user runs compile main.c and asks for the output to be sent to the log, it's perfectly okay, according to the ACL model, because it says that the compiler has write access to the log. So the original example of this, which is that you would create a program that when you compiled it, the output was a billing record that gave you a giant refund. You would do that. It would write the refund. Actually, that's not quite true because it can't quite do that. But you could. Yes, you can. Yeah, potentially, because it's going to write this to the log file, so it can write the. You work out what format the refund entry is, and tell it to write a log.txt instead of a.out, and it has write access to log.txt, and it writes you a refund of $1 million, and you go away and you're fine. And that, according to the access matrix, is fine because the compiler has write access in exactly the same way to both these files. So as long as you can persuade it that as long as you can make a program that when you compile it looks like a billing record, you're good. So the ACLs don't seem to authorize correctly, and that's this is the kind of core problem that this paper is about. The capability model, on the other hand, is fine because if you look at the file descriptors in here, it's always file descriptor 3 it's writing to log entry. That's what the compiler program that the vendor has written for. It's the vendor owns the compiler program, and it always writes to FD3, and FD3 is always passed in by the vendor. And it was created with FD3 passed to it originally when it was created. So in the capability model, there's nothing, you can't actually persuade it because you're not giving it a name, you're just passing in an output, and it's always going to use the output for the right thing. And so the capability model is correct and the access control model is not. And that's kind of weird because the original paper said, these two models are exactly the same, one of them is more efficient under certain circumstances, doesn't matter what you use, it's okay. And so the paper comes to this conclusion that actually the models are different, and they're not the same at all, and they use different parts of the access matrix at different times, and they make changes to it in different ways. So this, although it kind of looks the same, it's not really the same because it's actually got more information in there at the point where it's making the decision. And the other really important thing is that it matters that there are 3 parties involved here. In the cases that the original paper looked at, there were just 2 people. There was just someone asking for access and someone granting access, and that was okay. But in this case, there's a 3rd confused party, which is the compiler. And so it's in the presence of like 3 people trying to work out, or 3 programs doing this, you get the problem. And so having 3 people involved is kind of common. I mean, I think that I'll come back to microservices a bit more later, but in the case of microservices, there's always 3 services. There's not just 2 services. There are lots and lots of services, and these kind of issues actually are coming up more and more, where it's not just a really, really simple case of I come to the computer and I say, can I access this file? And it says yes or no according to the matrix. That's the case where there's 2 of us. There's me and the computer saying yes or no. Computer says no. That case is fine, and there's never any problem with that. And that's the way that the other papers originally looked at this problem. And it's only once you get to this stage where you've got the vendor, the user, and the compiler that you suddenly realize there's a problem. And I'm not going to talk about this now. I'm going to talk about that later. I'm going to talk about the examples. So the examples in the paper were the ones that were really important. Yes?
There seems to be some sleight of hand here, though. Like this compiler object comes from some other trusted party, right? And
well, the vendor has.
That, like once that FD3 has been put inside that compiler object by the vendor, then the user can't have any API to that object to change it somehow.
Yeah, well, this is why I've tried to write these for both of the cases, what the API calls look like. So the user's API call, unless you actually, I mean, obviously if you subvert the thing and you find some backdoor, this is the issue you brought up at the beginning. This is not a case where you're actually managing to totally subvert the program by doing a buffer overflow and making the program run something else. This is a question of what you can do with a normal access call. So with these access calls, use FD3 because you can only pass file descriptors, not you can't say I want to use the thing you have as FD3. You're actually giving it a thing. You're actually giving it a file descriptor and saying use this file descriptor for this as FD.
I don't think you need buffer overflow, right? This compiler object is some code that's coming from somewhere, and the paper kind of says, oh, it's coming from somewhere trusted, right? But
No, it specifically comes from the vendor. The vendor is creating this because the vendor is offering this compiler as a service. It's not coming from the vendor is giving you a compiler. So the vendor is creating a yeah.
It doesn't. I think what I'm saying is it doesn't compose very well, right? So if you're taking this compiler object from somewhere, the user's taking some code together in some way, it doesn't tell you how to solve the hard. Like basically, there's magic in this compiler object that does the right thing. It doesn't tell you how to compose those objects with other things. Essentially, it's the code provided by other vendors where they can all write to that log file in a secure way without letting you swap it out for another capability.
But you can compose them as separate services that have access or no access to the log file. But you can't run arbitrary code in the compiler and expect it to be secure.
They said, oh, you put FD3 in there and you kind of can't get it out again. And that's all right. And it's all right in the system, that's all right.
I'll talk about a little bit about that, I think, later on, a little bit. But we can talk about it a bit more in a minute. So so cross-site request forgery is a situation. You've got the browser is the party in the middle, and the kind of classic example is that some website you're visiting knows that you're logged into your banking site and will send a post request to the banking site saying, please transfer money to a hacker in Switzerland, please. The browser has your cookies. It sends them with the request to the banking site, and you basically, it looks like a perfectly normal request. It looks like you just posted that. I mean, it can be a form on the site you click on, and you just click on it, and it looks. But the form actually refers to a different site. This had become a big problem around when this paper was created, and the solution that everyone still uses on every single form you ever go to now has a random token that is only available when you're on the real site. So you have cookies that attach to your banking site only and can't be submitted from any other site, and that cookie is just a random string, and the real site will submit that with the request, and the other site won't be able to. And this kind of random token acts like a capability in the sense that it's an additional token that says this is the real site, and I should be able to do this action from this site, and which you don't transfer to any other site. We'll talk a bit more about other ways that you can create capabilities a bit later. So the solution was to effectively build something that looked a bit like a capability, but kind of disguised. And there are other examples, talk about clickjacking, click fraud, and various other things that are very similar things. And these problems are still kind of real in the browser world. We just got used to having to deal with the weird solutions that people tell us to do about adding these random things, and people actually often forget exactly why they have to do those things. But the security model just requires that these things be like that. Looking at the present, a recent example, this kind of the reason I kind of decided to do this talk was late last year, Kubernetes had a big CVE. And it's a sort of, it's actually a kind of mixture of issues that are very related to this and a few. So Kubernetes is an API server that aggregates a bunch of APIs, so it's a very classic intermediate party. So if I want to talk to some API over there, I go to the API server and say I want to talk to that API, and it goes over there. The actual hack was to make a connection and then do HTTP 1 upgrade onto the connection, which would then let you then basically you would do a normal API server connection to some API server that you had some access to, and then you would do an upgrade and then send it some more commands that the intermediate server didn't know you were doing. But the connection to the other thing would be the API. The API server would the API server basically is totally trusted by any component to be any user. So it can pretend to be you, or you can pretend to be any other user, and the connections from it are totally trusted because it's the API server. So that's a kind of example where there are three things, and we've got an intermediate problem, but we've also got a problem of having an object that's like totally super privileged, which is something and not a least privileged thing. So it's a kind of weird mix of these things. And high and low privilege API requests basically all go through exactly the same path, and they look the same. And it's just the API server is just allowed to say anything. I'm any user. I'm any kind of thing, and everyone just has to believe it because it's got its credentials. Basically, say I can do anything. So once that request's over there, you can go and say, oh, and by the way, I'm an admin. I want to basically do anything I want to do. If you can keep the connection open and turn extra commands down it. So it's not exactly the exact same situation because there's a sort of hack where you send this upgrade thing to keep the connection open and send other commands along it. But it's very similar. There are three parties. One of them has more privileges than you do, and you manage to get to act with its privileges, and that's kind of very similar. I just said that. So why has nothing really changed? Why are we still getting these kinds of issues? It's good to have next case soon. Role-based access control is still exactly what everyone does. The whole kind of principle of how we do access control in general hasn't changed. The browser's got these issue mitigations because the browser platform has been the platform that's had most work around security for this in this time. But we're entering this world with microservices and serverless and lots of things with lots of parties, and so it's becoming more severe. Kind of important to kind of think about what these capabilities really are. I talked about signed URLs and file descriptors and things like that. On a kind of local machine, you can consider capabilities just to be objects. As you have access to an object, then you can call methods on it in a programming language, and or things like file descriptors that the operating system will give you. If you don't have a file descriptor and you don't have ability to open files for some reason, then you can't create one. This doesn't kind of work in the distributed systems, but in local systems, that's kind of the way. And there's been a load of good, really interesting work. There's this project called Capsicum, which is in FreeBSD, and which Google said they were porting to Linux about 2 years ago, or 3 years ago, or 4 years ago, and nothing's happened, which extends file descriptors so you can do even more things with them, and has process descriptors, which are file descriptors for processes, so you can create a child process, and you get a file descriptor pointing at it, which you can then pass to someone else. Really cool. Probably never get implemented in Linux. JavaScript, there's this thing going through standardization at the moment called the Realms API, which is really cool, which basically takes away, lets you basically disable global variables in JavaScript so that you can, and the ability to just access anything in the standard library, and just you can have a function that can only access exactly which standard library functions or objects that have been passed to it. So you can basically have something, you can create a function, you can say import a package which has no access to the DOM in the browser. It only has access to an object you pass to it, which might just be able to do a little bit of computation or something like that. So, for example, you can do things like you can stop some random package import being able to read your encryption keys and send them off to an attacker or something. There was lots of cases like this with NPM of people doing targeted package hacks and things like that. So there's loads of good work going on there. In most programming languages, it's kind of difficult because you can just refer to, like, in most programming, in Node, you can just write something to the network from any program. You just import networking and you can just write to the network. But this basically sets it up so you can't do that, and it's really nice. And so JavaScript actually, with this, actually have some really nice security properties and be really useful for doing things, which is kind of surprising, given that people generally think of JavaScript as a not so useful language from this point of view. Distributed capabilities, though, there's been a bit less work. API signing on AWS, not used much, mainly, as far as I can tell, mainly available for S3, not everywhere. JWT can be used as a capability system. It's basically signed bearer tokens. It's not generally used like that. It's generally used as a login token. Perfectly usable as a capability system if you want, but it's not really documented how you do that. So basically, yeah, it would be nice if there was a more understanding and documentation about how you can use it like that, but it's definitely entirely possible. So basically, it's just a signed token that says you can do X, and you can pass it around and then eventually do X with it. So very much a capability. There's kind of different mechanisms you can actually use apart from the sort of JWT type signatures. So the original, if you look at the old capability papers, they talk about Swiss numbers, which are effectively, I don't know if this was ever true, but if you've got a Swiss bank account, you could just access it by giving them the account number, and it was just a presumably unguessable number. It's no good if it's very short and you can, account number 3, please. So just pick a long number. That's effectively what the CSRF cookie thing is. It's just a random string that you can't guess. So you can use that by passing it around, and then the other end says, 26. That's a good, 2646521. Yeah, that means you can access this. You have to obviously be careful not to put those in unencrypted connections or accidentally write them on the wall. Signed things, again, they have the same problem. You mustn't use them in unencrypted connections. But you don't have to, the service at the other end doesn't have to remember the number. It can just look at the signature and say, is the signature good? And if so, what's this person supposed to be able to do? Oh, they're supposed to be able to read they're supposed to be able to write to the log.txt file. Okay, I believe them. They've got the thing that says they can do that. We don't hand this out to anyone. There's macaroons, which there's a really good paper, which I highly recommend if you like papers about this kind of thing. Macaroons cookies with contextual caveats, written by Google about 5 years, someone at Google about 5 years ago, maybe 6, maybe slightly longer than that, but after this paper. Again, these use signing to say what you can do, but you can add more and more restrictions. So you can have a thing that lets you access a file and do anything with a file, and then you can add a thing saying, but you can't write to it. And then you can turn that into a token that just lets you read the file, give it to someone else, and then you can add another thing that says, you can only read the file between 5 and 6 in the afternoon on Thursdays, and then you can add that and you sign that and so on. So they're kind of fun. They can get kind of complicated, but definitely recommend the paper. And then you can use asymmetric encryption. It's something I've been working on a bit with capabilities. This is kind of very early stuff that I've been looking at, but the advantage of that is to combine the encryption and the capability in one handshake, so that if you connect to the wrong person, you don't just give them all your credentials in the connection. So it's really important, obviously, with something like JWT, that you don't just connect to the wrong site or forget to check the TLS certificates from the right person or anything like that, because you'll just be giving a credential that someone else can use to access your stuff. Whereas if you do it with asymmetric encryption and do it as part of the encryption handshake, you can basically, they won't get anything if the connection fails, which is, I kind of like it as a security guarantee, but this is all kind of researchy stuff. I promised someone I'd put a bad pun in here. So I think one of this whole kind of thing about identity and things is really confusing. When you're logged into the computer and you're typing on the command line, or you're in a, manipulating things directly in a user interface, you tend to think that those things are being done by you, those commands are run by you. I'm logged in as Justin on this Mac, and I type things, it says Justin, and I open a file, and I think Justin is opening the file, and I think that Justin on the computer is kind of me. But it's not me, actually. It's the Bourne shell. That's the actual thing that's running the program. I just trust it to kind of do things quite a lot, because I can see that it's doing what I type, I guess. And so there's a very high degree of trust, but it's not, and I think, I don't think, oh, what permissions shall I give my shell? What shall I allow it to do? I just think it's me. I think of it as me, and it has access to all my stuff, and all my stuff is on the, that's on the computer, and I kind of treat that as okay. I once gave a whole talk about Charlie Chaplin's Modern Times, so I'd like to have. There aren't actually any people inside the machine. It is actually a computer, and I think a lot of the thinking we have around identity and authorization and things comes from all our experience with the web, which again has done all these things really well and seriously, and lots of people have spent a lot of time. W3C has had, has for many, many years has been thinking about identity and authorization, and we've kind of internalized these things because we use the web all the time. But it doesn't really apply in the same way to things like microservices. When you're running, if I'm running a service in AWS, it's not me, it's a program. It's doing things on my behalf, but it definitely doesn't feel like me, and we shouldn't treat it as being, the user shouldn't be Justin anymore, and we should think about machines. And there's sort of halfway concepts like service accounts, which is something that Google has pushed very hard in terms of the authorization model in Google Cloud. And service accounts are like, this program is another kind of person. It's like you can, it's got an account, you can see what it's doing, and it's like you, but it's it. And that's kind of one way of doing it, but it's a sort of halfway stage to thinking about what access do I want, what capabilities, what access do I want to give this program, what do I want this program to be allowed to do, what's the least I can give it and actually have it work, and not, this computer's a person, this computer's me, it should be able to do everything I can do, which is not the right way of, we've ended up with this kind of model that 10 years ago someone realized was kind of a mess, and I think it's still a mess. And we need to think about these things. It's really important to think about these things and work out how we're going to do these things in future. And also, even if your paper wasn't accepted in a conference, people might still like it. So, yeah, questions. And
What's the Kubernetes response to changing RBAC, or is it just kind of patching?
They patched the thing. I don't think there's been any kind of, I mean, I wrote a blog post about it at the time saying it was this kind of problem, and but
So would you rip out RBAC?
would you rip out RBAC? I mean, I don't know. I think there's two bits. So the first thing is things that can pretend that they're any user have total root, basically root credentials. The things like doing sudo or locally, where it can then absolutely have total control over everything, which is the same as the Kubernetes API controller. That model is definitely wrong. That's more wrong than anything else, because if you just, if you give something like total power over everything, and then it's a tempting point to subvert requests to there. And we've had this whole thing in Unix with programs that you have that suid root and can do stuff that they are your attack surface. You attack those things first, because when you break them, you get total power over everything. And with like Unix and things, there've been enormous numbers of those where those things have been a problem. And if you look at systems now, they have a lot fewer of those things. And so that first. So the first thing is to just get rid of things that can do anything and have total power, and have public APIs that you can talk to, and then that anyone can talk to, because you don't really want to be able to escalate privileges like that. Should you get rid of RBAC is an interesting one. I mean, I think that it's something that people are very familiar with and understand, and so I think it's very difficult to just say don't use it. But I think we need to start. I think we need to start by saying the things I was saying at the end, that these computer programs are not people, so they shouldn't act as people. They shouldn't have people's access rights. So I think moving to things like services counts as a good intermediate step. But we need to seriously look at those situations with three parties and say these ones are just broken, and these are going to be problematic, and we should then start moving, define it, having more interfaces. So on AWS, as far as I can tell, only S3 supports signed URLs. You can't have a signed URL to a Lambda or anything else, and no one understands the AWS access control system, which is basically the RBAC system. I mean, literally, they have. I spoke to someone who was working on automated tooling for telling people they've got it wrong, because everyone does, and you can tell by looking at it. You can run a computer program that tells you that they've obviously written something that is not what they meant, because one of the rules overrides the other one, and it's like. So, I think we're going to have to approach the problem kind of gradually.
I think it's hard to separate them like that. I think the reason you've got these kind of programs with this amount of power, like root or the API service, because it's really hard to know what else to do. And so unless you have architectural training,
No, you do. Yeah.
No,
you do have to have them, but you can. I think that the kind of model that we've ended up with in Unix is that things go down. So things that when the computer starts are running as root, and then you obviously have to be root to run the login service. So that's the user login, but then it stays as the user, and the user doesn't get to escalate back up to root anymore. And if the user has to escalate, then you try and take it through a path that only gives them exactly the permissions they need, not give them back everything again. People don't always use it like that, but I think that's more the model we've been aiming at. You clearly have to have privilege for it. You have to have the components that give out the capabilities in the first place. And there's, but you want those things to be kind of small and trusted, not giant and having loads of interfaces and doing non-privileged and privileged things and so on. I mean, you want a small, all-powerful piece that you just use occasionally, and not a huge, all-powerful piece where all commands go to.
It seems that historically ACL models have been more widespread. Does capability model have any downsides that
I think people find it confusing. If you look at the first thing that when you tell people about capabilities, they say, but you can pass them on to other people and they might do bad things with them because they're transferable. And I think it's this paper that has, not one of the other ones, that has the example of having let's call it a Google Doc, where someone creates a document and they give their co-worker access to it because they're writing a paper together, and the co-worker gives it to their student, and the student write some rubbish in it, whatever, and they say, oi, but with the let's give them names. Alice has a document. She gives it to Bob to write some bits. Bob says, don't know what to do, gives it to Carol. Carol writes something that's wrong in it, or whatever. Alice says to Bob, why did you write with Bob's credentials? And because it's a capability to write to the document. And you know it was Bob because that's the only person you gave them to. Like, Bob, why did you write this? And I was like, I didn't. I gave it to Carol, and Carol right there. It's like, there's less traceability in the sort of sense of it in that sense. And if you've delegated someone, you've kind of delegated it. But delegation's really, really useful. And I think there are ways to do a mixture of delegation and audit. But I think it's an interesting thing that people definitely want. Kind of government, NIST has all this stuff about access control, and it's all, a lot of it's from the historic kind of Department of Defense security models which are all about people, you know, top secret data and people with security clearance and those kinds of things, and you mustn't be able to pass stuff up and down, like multi-level security and things like that. But that stuff, it doesn't really correspond to what real people use on a day-to-day basis in any kind of useful sense, even though that's what SE Linux is supposed to be for. So, did I answer your question?
I was also wondering whether there are any performance downsides for using capability model versus ACL model.
It kind of depends how you implement it, I think. I mean, I think that if you're using some encryption or signing, potentially, yes, but it's probably negligible compared to the amount of encryption you're doing anyway nowadays if you're encrypting things, because encrypting things is a good idea nowadays. So I don't think it's necessarily any worse, but potentially, I mean, at the time, it's interesting if you read the literature, most of it was written, the early capabilities literature was written when cryptography was not actually very cost effective at all, and it's still kind of weird when you read it. It's like, oh yeah, these people had heard of public key encryption, but it was not possible on their computer because it was too slow. So I think generally probably not. You can always get in touch with me. I'm Justin Cormack. I'm Justin Cormack on most internets. And yeah, I highly recommend you read the paper. It's short and easy to read, and it's interesting.